Okay, let's get right into it. I'm Jacob White, and this is my Lab 5 presentation. Introduction to Lab. In this lab, I'm going to analyze the motion of a rolling object released from rest on an inclined plane. To do this, I'm going to film the motion of a basketball rolling down my driveway and then create a model. To create the model, I will use the program Tracker to calculate the initial and final conditions needed to run the model. I will then create code that separates the parallel and perpendicular components of force, allowing for deeper analysis into the forces involved in the motion of the basketball. This lab is important because it will allow us to better understand how the underlying physics principles dictate the motion of a simple rolling object on angled surfaces such as a car tire or a basketball. I use this model as it makes it easy to visualize the components that contribute to the net force. So here's the fundamental physics used: Newton's second law, the momentum update formula, and the formula for frictional force. At the bottom you can see a diagram of a simple inclined plane. So here's the video of the motion. There's my mom letting go of the basketball. There you go. So here are the initial conditions: the diameter of the basketball, the mass, the length of the road, the angle of incline, and the time step. Coding. I used the Lab 1 starter code as the template for the code. However, I needed to make many changes to accurately reflect the conditions of the rolling basketball. First, I changed the initial conditions, such as the mass, time step, initial position, etc., to match that of the tracker video. In this scenario, the perpendicular net force and the normal forces cancel out, as they're equal to each other, leaving just the parallel net force and friction force. I tried many different ways of defining the net force in terms of the parallel net force and the force of friction. However, I could not get past the many coding errors that just kept popping up. So instead of coding the net force in terms of the variables, I decided to calculate the net force and the code as a numerical value, just to simplify it so that I don't get all of those errors. So to calculate the magnitude of the net force, I use the equation Fnet equals Fnet parallel minus the force of friction. So Fnet parallel equals the mass of ball times g times sine 8 degrees, and the force of friction is equal to a times the mass of the ball times g times cosine of 8 degrees, where a is the coefficient of friction. The direction of the net force is in the parallel direction, which is defined as the vector cosine 8 sine 8 0. The value a was found by matching the final positions of the tracker data with the model to get the most accurate match. So a, also known as the coefficient of friction, was determined to be 0.064. And then later arrows representing the parallel and friction forces were added. So here are the equations behind the code written on paper. It might be a little bit easier to understand in this format with the variables listed at the bottom. So here is a plot of the model versus the observational positional data, where the model is the blue line and the observational is the red line. So they're very close, as you can see. Data analysis. So as can be seen in the graph, the positional data gathered from tracker and the positional data gathered from the model are very close for the motion of the basketball. Of course, it must be noted that I calculated the coefficient of friction by trying to match up the final positions of both data. So of course, the final positions match each other. The model seems to lag behind the observational data until the final time steps. This is likely because drag and the translational kinetic energy converted to rotational kinetic energy were not accounted for in this lab. So to improve the lab, I should account for these factors, and this would likely result in model positional data that is closer to the observational data. So why not use the y positional data? I decided not to include the y positional data in the graph or the analysis of the motion. This is because the distance that the basketball moves in the y direction is quite small. As a result, small discrepancies in the point mass tracking could lead to very large differences between the observational and model data. This creates a large margin of error that really invalidates the comparison of data. And that concludes my lab.